This lesson is about the calculation of the confidence limits for the systematic measurement error and the test for significance using the student's distribution. And hello again to this lesson, which essentially has two learning objectives. At the end, you should have understood why the test for significance is necessary for the systematic measurement error and how this is derived. Furthermore, you should be able to use the t-distribution to determine the required values for the test for significance yourself. This lesson is divided into two chapters. In the first chapter, we discuss the fundamentals needed to assess the significance for the systematic measurement error. The focus here is on the mathematical formulas and their understanding. In the second chapter, we determine the quantiles of the t-distribution for different probabilities and sample sizes that are required for the test for significance and use them in example calculations. Let's start with the basics needed to assess the significance for the systematic measurement error. One of the most important tasks in process monitoring is to measure the manufactured product characteristic. A suitable measuring instrument must be used for this. For this purpose, proof must be provided that the measuring instrument is suitable for the measuring task. This proof includes, among other things, determining the systematic measurement error. This is defined by the formula with the vertical dashes, where x bar is the mean of the sample. In this case, random sample means that the 25 measured values in the table on the left were all measured with the same measuring instrument on a part on the same characteristic and by the same person. xm is the reference value for which the measurement deviation is calculated. This reference value is obtained, for example, by measuring the characteristic to be checked with the measuring instrument with a significantly higher measuring accuracy. Small s is the standard deviation of the 25 values in the table. For the systematic measurement error, it is irrelevant whether the mean value is greater or smaller than the reference value, so whether the sign is positive or negative. Only the absolute value or the absolute amount counts. This is what the two vertical lines in the formula stand for. The question now is how good the estimate for the systematic measurement error is. Is this estimation in the expected range? Basically, the larger and more representative a database is, the better and more significant are the conclusions that can be derived from it. Conversely, this also means that these conclusions always contain a certain degree of uncertainty. To take this uncertainty into account, one does not simply state an absolute value, but also says that the actual value is to be expected in a certain range. This range is called the confidence range. A complete statement would therefore be the following example. A mean diameter of 60.1 mm was calculated based on a random sample of 25 parts. With a probability of 95%, the actual mean diameter of the population can be expected to be in the range of 60.09 to 60.11 mm. The formulas for calculating the confidence limits differ depending on the parameters for which they are to be calculated. The formula for the confidence intervals of a standard deviation is different than for the range, and that for the mean is different depending on whether the variance is known or not. The formula shown is for the expected value of a normally distributed characteristic, such as the mean with unknown variance. In other words, based on the estimate of x bar for the sample, the actual mean will fall within these limits with a given probability. Now that the interrelationship around the confidence limits has hopefully become clearer, it is now a matter of concretely answering the question of whether the systematic measurement error is in the range that is to be expected. From this question arises the further question of whether the reference value xm of the standard lies within the calculated confidence interval. A quick reminder: the reference value xm was determined by measuring the diameter with a very precise measuring device. This diameter is 60.1030 mm. The same diameter was measured 25 times with a less precise measuring device. For this less precise measuring instrument, it is to be determined whether it is suitable for the measuring task. The measurement results are in the left table. Their mean diameter, x bar, is 60.1013 mm. With this x bar, the quantile of the t-distribution and the standard deviation, the confidence limits can now be calculated. If the reference value xm is then within these confidence limits, then μ is equal to xm. If the reference value xm is outside the limits, then μ is not equal to xm. Substituting xm and transposing the formula, we get the following relationship. The left part of this equation is the systematic measurement error. Now, two hypotheses can be put forward. The first hypothesis is that the reference value xm is within the confidence interval and therefore μ is equal to xm. This is called the null hypothesis. If the first hypothesis is not true, then the alternative hypothesis applies, that μ is not equal to xm. The null hypothesis is accepted if the systematic measurement error, calculated from the reference value and the mean, is equal to or smaller than the product of the quantile of the t-distribution and the standard deviation. If the condition of this equation is fulfilled, then the null hypothesis is accepted. This proved that the result is within the expected limits. So it does not deviate significantly and can be accepted. However, if the condition of this equation is not met, then the result is not within the expected limits. The result deviates significantly and cannot be used. In such a case, actions must be taken that leads to a measuring instrument that is suitable for the measuring task. So, hopefully, this has made it a bit clearer why it is necessary to test for significance and how to do it for the systematic measurement error. How to calculate the quantiles of the t-distribution for different sample sizes and calculating confidence levels is the subject of the next chapter. In this chapter, we find the quantiles of the t-distribution ourselves for different probabilities and sample sizes, which are necessary for the test for significance. We do this in different ways and apply the results in a sample calculation. In the previous chapter, we saw that the quantiles of the t-distribution are required for the calculation of the confidence intervals and the test for significance. We will discuss three different ways to solve this. First, we will take the required values from a table. In practice, this will be the most common way since these tables are available in large numbers in specialist literature and on the internet. However, these tables must also be understood and applied correctly. Second, we will calculate the quantiles ourselves, which we have previously taken from a table. We use the MS Excel function t.inv for this. And lastly, we will calculate one of the limits of the confidence interval directly. For this, we use the MS Excel function confidence.t. Let's start with the first approach, where we will take the quantiles from a table. The framework conditions defined on the left apply to this. The confidence level 1 minus alpha is 95%, or the significance level alpha is 5%. This means that the probability of having a significant result is less than 5%. And we want to find the quantiles for a sample size of 25 and 50. First, let's look at the top distribution on the right. With our chosen confidence level of 1 minus alpha equal to 95%, 95% of all values are to be expected between the limits drawn here. The remaining 5% are outside these limits. 2.5% on the left and 2.5% on the right. These threshold values, or quantiles, are tabulated, but often only for one-sided limited distributions. A change must therefore be made. To do this, let's now look at the image below on the right. There is only one limit here. 2.5% of the values are on the right side of this limit and 97.5% on the left. Thus, for a 95% confidence level, either the column for 1 minus alpha equals to 0.975 or for alpha equals to 0.025 must be found in the table. Since the quantile of the t-distribution depends not only on the confidence level, but also on the sample size, the applicable sample size must now be selected. In our example, this is 25 and 50. Here is a small excerpt from the table for the quantiles of the t-distribution for different significance levels alpha and degrees of freedom f. For alpha, 0.025 and a sample size of 25, the quantile is 2.064. And for a sample size of 50, the quantile is 2.010. This is what a complete table for the quantiles of the t-distribution looks like for different significant levels alpha and degrees of freedom f. So you must know the connections between the two-sided confidence levels and the tabulated one-sided quantiles to be able to use these tables correctly. Next, we will use Excel to calculate the quantiles just read for alpha equals to 0.025 and n equals to 25 and 50 respectively. For this, we use the Excel function t.inv. The conversion from the two-sided limited distribution to the one-sided limited distribution must take place here in the same way, which is why the representation on the right side remains valid. But be careful. The Excel function t.inv returns the left-hand quantile of the t-distribution. Therefore, 0.975 and not 0.025 is entered for the probability in the probability input field. With a sample size of 25, the degree of freedom is 24. The result is a value of 2.06, 389 and so on, which is the same as the quantile we just read from the table earlier. The same applies to the sample size of 50. In the picture on the right, the quantiles just calculated were written again under the t-distribution. The mean μ here is 0. Because of the symmetry, the left and the right quantiles are the same in absolute values. With the values determined in this way, we will next carry out the test for significance for the systematic measurement error. Here on the left side again our example with the corresponding values. We have just determined the quantiles. The reference value xm is the diameter of the piston measured with a very precise measuring instrument. The diameter of the same piston was measured 25 and 50 times with a measuring instrument for which we conduct the MSA. The mean diameter x bar for both samples is 60.1013 mm. The standard deviation S of the two samples is 0.0045 mm. We already know the formula for the significance test from the first chapter. Here it is again clearly represented with its individual factors. On the left, the systematic measurement error, then the quantile of the t-distribution, and the sample size and the standard deviation. In order not to repeat the entire first chapter, the following is only briefly repeated. Significance testing is about checking whether the equation is true or not. If the left side is equal to or less than the right side, then it is satisfied. This means that the result is within the expected limits, so it does not deviate significantly and can be used. Otherwise, it is significant and cannot be used. On the right-hand side, the systematic measurement error was first calculated. This is 0.0017 mm. Then, for a sample size of 25, the right-hand side of the equation was calculated. This is 0.0019 mm. This satisfies the condition that the left side of the equation should be equal to or smaller than the right side. The calculated systematic error is not significant and the result can be used. Let's see what it looks like for a sample size of 50. The larger sample size and quantile that applies to it results in a value on the right-hand side of the equation of 0.0013. This time, the condition of the equation is not fulfilled. The left side is larger than the right side. The calculated systematic error is significant and the result cannot be used. Now we come to the third and last possibility for this lesson to determine the factor for the standard deviation required for the significance test. For this, we use the MS Excel function confidence.t. The result of this function is not a quantile, but directly the confidence level for a standardized standard deviation of 1. The value for the significance level of alpha is 5% and can be entered directly in the input field with 0.05. As expected, the underlined values are the same as we had just in the previous example. You can avoid this intermediate step by not using the standardized standard deviation of 1, but the actual one from the sample. This gives you the underlined and already known values of 0.0019 and 0.0013. The assessment is carried out in the same way as previously described. At the beginning of this chapter, we saw the table for the quantiles of the t-distribution for different significance levels alpha and degrees of freedom f. Corresponding values for various levels of significance are also summarized in tables for the values just used for the confidence intervals. An example is shown here and can also be found in the relevant specialist literature. After this chapter, you should now be able to use them professionally. Well, that was a lot of new information. Therefore, I would like to conclude by repeating the 4 most important key messages. The systematic measurement error is calculated based on a random sample. The test for significance is intended to demonstrate whether the calculated systematic measurement error is within the expected limits. If the value is within these limits, the result can be used. If the value is outside, then the result is significant and should not be used. If you found this lesson helpful, please let me know and leave a comment. Thank you for that, take care, and see you next time. Bye.